Thank you very much, Daniela, and thank you also, Avindra, for having me in this very interesting workshop. The topic of my presentation, enhancement of concrete barriers resistance to projectile impact, refers to protective structures, whether military or civil. Now, most of these protective structures are constructed of reinforced concrete. And the reason for this is because reinforced concrete provides these structures with global resistance to reflected pressure from blast waves, but not less importantly is that it provides them also with local resistance to penetration of striking fragments of projectiles. So this presentation focuses on the resistance of protective reinforced concrete barriers to penetration and perforation by non-deforming projectiles. The concrete type in most protective structures is normal sand concrete. Now, there are many studies that indicate that with respect to mainly penetration and perforation resistance, concrete uniaxial compressive strength is the most representative parameter, where the resistance is proportional to the compressive strength, which is raised in the perforation formula to a power that ranges between 1/2 and 2/3. And so considering that resistance is proportional to the compressive strength, and with the introduction of high strength concrete, the material's increased strength has called for its use in barriers that have to resist impact. The hypothesis regarding the effectiveness of using high-strength concrete for protective structures was not trivial, though. However, our initial laboratory findings at the Technion, as well as others, supported this hypothesis. As you can see in the graphs on the right-hand side here, we found that increased concrete strength yielded lower penetration depths, indicated here by these black points of high-strength concrete, and also higher ballistic limit. However, it also yielded larger rear face damage, as you can see by these black points here on this graph. So I already mentioned several criteria for assessment of resistance. Let's talk in a more orderly manner on these criteria. The resistance to impact of finite thickness barriers, such as walls or slabs, may be evaluated according to two main criteria. First one is the ballistic limit, and the other one is the damage. The ballistic limit refers to the barrier's ability to prevent perforation under projectile impact. In other words, for a given barrier thickness and non-deforming projectile parameters, such as its diameter and mass, nose shape, the ballistic limit is marked by the projectile's velocity, VBL, ballistic limit, or by its energy, EBL, at the limit, if you want, ultimate limit of just being breached by the projectile, just being perforated. As for the damage, the criteria of damage, and this is in plural because this includes it may include several parameters. The first one is, of course, the penetration depth, but this is relevant only in cases that the barrier has not been perforated. Other measures of the damage are the damage inflicted at the front face or at the rear, which is the protected face of the barrier. Alternatively, alternatively, I will just summing up for the damage. The damage criteria are measures of the barrier's vulnerability. They indicate the extent of the impact local effect, and they are an indirect indication of the ability of the barrier to withstand multiple hits, or if you like, it's the resilience of the barrier. So how do we quantify damage? You can see here two examples of two of our laboratory specimens. On the right-hand side, front face, on the left-hand side, rear face. And as you can see, there are several ways to quantify the damage. We can measure the damaged area. On the left-hand side here, you can see that we did this by taking measures of two representative diameters, the longer diameter and one perpendicular to it, and then define an equivalent diameter by the square root of their multiplication. Another way to quantify damage is to usually digitally measure this area and then compare it, normalize it with respect to the total area of the specimen, of the target. So this can be done at the front face, and if we use equivalent diameters at the front face or at the rear face, or as you can see here, we can also look at the an equivalent diameter that takes both front and rear face into account, an average diameter. Now, alternatively, we can also look at the weight loss of the specimen by, for example, in the laboratory, measuring the specimens before the test and after the test. And the difference in weight is the weight of the damaged material volume due to the impact. So in the following, evaluation of the resistance is presented with respect to the striking energy at the ballistic limit, EBL, and to the damage. Now you have to realize that the damage for a given projectile and a given target can be different depending on the energy of the projectile. Therefore, in the following, I will refer to the damage at the vicinity or at exactly the ballistic limit, at the energy of the projectile, which is almost EBL. The roles of the concrete strength that I mentioned before, but not only the strength, also the mixed ingredients and their effects on the impact resistance are evaluated with a focus on the influence of the aggregate types and sizes and the application of steel fibers. And I will start by showing you some results from our laboratory tests of single-layered specimens. First, let's look at the sketch of the experimental setup. We used a gas gun that was used to accelerate our projectiles. The projectiles were 50 millimeter in diameter with a conical nose. They had a weight of 1.5 kilograms, and they were made of hardened steel, which is why I refer to them as non-deforming projectiles. Then we had a device to measure the striking velocity, and then, of course, the target that was supported by a special setup. All our targets had the same dimensions of 80 by 80 centimeters with a thickness of 20 centimeters with the front mesh and the rear mesh. And under laboratory conditions, we could control that the striking projectile would impact the specimens right at the center in between the rebars. This is the experimental program for the single-layered specimens, and let me guide you through it. We looked at the effect of using steel fibers, either not using them or using them in a constant quantity. And so we had two types of control specimens without any fibers. One was made of normal strength concrete and the other one of high strength concrete. And then all the other specimens were made of high strength concrete with an average compressive strength of about 100 megapascals. Then we looked at the effect of the aggregate types. We had dolomite, basalt, and flint. And we also looked at the effect of the maximum aggregate size. And I will start with showing the results in terms of the ballistic limit. So you see here on the y-axis the values of the energy at the ballistic limit, EBL. And the first thing that we can see is that with respect to the control specimen that was made of normal strength concrete, increasing the strength, indeed increased the resistance, increased the EBL by 30 up to 65%. So this means that concrete strength matter, it increased the strength, but it is not the only parameter. And here's the other control specimen made of high strength concrete without fibers, and you can see that all the other specimens which had similar concrete strength had increased resistance from 3 to almost 30% with respect to this specimen, where we had an increase in the resistance to perforation by the specimens that included the harder basalt and flint aggregates that are indicated by the letters B and F. And the highest resistance was obtained with these aggregates in specimens that included aggregates with relatively large sizes, 50 millimeters, that are indicated here. As for the damage, in terms of the equivalent diameter at the front face, that's what we see here, we can clearly see that with respect to the specimens that did not include fibers, the plain specimens, all the other specimens that included steel fibers had reduced damage at the front face. And we have a similar result also at the rear face. Now, recalling that the highest resistance to perforation was obtained by these specimens that had the basalt and the flint aggregates, the 50 millimeter basalt and flint aggregates, this means that different ingredients could be engineered for different purposes by applying them at different layers of the barrier. And consequently, we have conducted another test series of double-layered specimens. We use the same dimensions of the specimens of the targets, but we cast them in two layers. The first layer that was cast became eventually the front layer here. And then on top of it, we cast what was eventually the rear face layer. The projectiles in this test series was a little bit heavier, but it had the same conical nose as in the previous tests, and it was also made of hardened steel. And again, let me guide you through these test program. We looked again at the effect of using steel fibers or not using them. And we had two sizes of aggregates that we denoted as small aggregates and large aggregates. Here we had only one type of aggregate that was made of, that was a dolomite aggregate. So we had 4 types of single layered SL specimens, either with or without steel fibers, with the small aggregates and with the large aggregates. Then we had specimens with 2 layers of equal thickness, 10 centimeters each. And then we had specimens with thicker front layer, TFL, wherein the front layer had the thickness of 14 centimeters, leaving only 6 centimeters for the rear layer, and the front layer had the larger aggregates in it. The results of these tests showed that the single-layered, plain control specimens with the regular coarse aggregates exhibited the lowest EBL, the lowest resistance to perforation. Then, by using large aggregates, we obtained an increase of about 20% in EBL. And by applying fibers or large aggregates in one of the layers, we had a further increase of the resistance to perforation by up to 35%. Then by using fibers throughout the thickness, another increase to up to 45%. And then in the thicker front layers with large aggregates at the front layer and fibers at the rear layer, but without fibers at the front layer, we had up to 50% increase, and finally up to 60% increase in EBL with fibers at the front layer. However, in some cases, increased perforation resistance also led to increased damage, increased vulnerability. So these results suggest that a barrier may exhibit a certain perforation resistance, but also a certain vulnerability. And the question is how to assess a barrier's comprehensive performance. And the answer for that is, of course, by considering both the ballistic limit and the damage. And this has to be done based on the understanding that the higher the required ballistic limit energy, and the lower the damage inflicted on the barrier, the better the performance. So based on this understanding, I've proposed to define a resistance index, RI, or if you like, you can also call it resilience index. And the way it is defined is by the ratio between EBL and vol D, which is the total damage volume. And you may note that this, according to this definition, the RI in the resistance index has units of stress. So let's look at the results of the double-layered series in terms of RI, which are shown here on the y-axis in units of megapascals. So the first thing that we see is the lowest RI plane specimens had values of about 5.5 to 7.5. Then we had an increase of RI values by addition of fibers at one of the layers. Further increase in the specimens was obtained in specimens that either included fibers throughout their thickness or had a thick front layer with large aggregates and fibers at the rear layer. So now the values of RI are increased up to about 20 megapascals. And then the highest RI values of about 23 was obtained in the specimen with a thick front layer with the large aggregates in it and the steel fibers that were applied throughout the thickness. And this brings me to the summary and conclusions of this presentation, that findings from experiments that were performed at NBRI of single-layered specimens suggested that a protective barrier may be engineered to have layers that utilize different mechanical effects of the mixed ingredients to produce better performance under impact. Consequently, results from double-layered specimens have confirmed this idea to a certain extent and have shown that certain configurations increased perforation resistance, but also led to increased damage. A resistance index, or again, if you like, resilience index, has been proposed to quantify the comprehensive resistance considering both EBL and the inflicted damage. It is shown that in terms of RI, the lowest resistance was of plain specimens, and the highest one was of the double-layered specimen with a thick front layer that comprised large 37 millimeter, in this case, aggregates with steel fibers throughout its thickness. And as an overall picture, if we plot on a y-axis the resistance or the resilience, and we plot on the x-axis the timeline, then from the very ancient times where people used brick or masonry for the defense walls, and then jumping ahead to the time where people started to use reinforced concrete, we could increase the resistance of our protective structures, defensive structures. Then by introducing high-strength concrete, we could further increase the resistance. And finally, by engineering the high-performance concrete, we could get even further increase in the resistance. Before I conclude, I would like to acknowledge the people with whom I collaborated in obtaining the results that I presented here: David Yankelevsky, Amnon Katz, David Ben Amo, the late Hanoch Yegerman, and of course the people who provided the most needed technical support, Menachem Siman and Elchanan Yitzchak. And with this, I thank you for your attention, and perhaps we can have the discussion with the background of the city where I come from. Thank you.
Thank you, Professor Dancygier, and thank you for staying exactly on the time of 20 minutes. It was fantastic. Thank you so much. I received some questions, so I would like to pose the first one. This is there a method of structural design for resistance index, or do we resort to trial and error design through experiments?
This is still under study. In fact, this resistance index is a relatively new concept. So being a relatively new concept, it has not been yet been applied in an orderly design procedure as you were asking. So this is still being studied.
Okay, and thank you. And then there is another question about what measure is put in place to prevent slip between the layers of the sample. I think I saw some rebars connecting them. I didn't see.
Not really. No, not really. So, no, the two layer specimens were cast wet layer upon wet layer. We didn't even wait for the first layer to be dried out or to cure or anything. We cast them wet, one on top of the other. Of course, there is more room for further study to see what are the effects of connecting these layers, or maybe put some types of boundaries between them. But no, we have not done this.
Okay, thank you. I think we have the time for a few more questions. So these are more related to fibers. So I will pose, they come from different participants, but they're all in the same context, so I will pose them all together. One is about the use of PVA fibers instead of steel fibers, if these fibers have ever been tried. And then the other question was about the fibers. Would you propose to use them only in the front face or in the rear face, on both faces? Would you have any comment on that?
Okay, I will start with the type of the fibers.
See.
When I started this presentation, I showed some initial results that we had with these small graphs that I hope you could at least see what's in there. And in these initial tests, we used several types of fibers. At that time, the results indicated that with respect to resistance against perforation, steel fibers are the best. They had the best influence and the most influence on the results. So I'm not sure about other fibers. At least we have not tested them. We have tested only steel fibers. In fact, also the type of the steel fibers could be looked at. There was another experimental series that was not included in this presentation, but it is published, it is there, about using a hybrid mix of but again, steel fibers. So I would go for steel fibers when we talk about preventing damage against impact and preventing resistance, but even this can still be further studied.
And there was another question that
as
was about natural fibers, but you answered that already. So you tested so far only steel fibers, and you would recommend steel fibers for these applications.
At least according to the experimental results that we and also other people have so far.
Yes.
There will be further studies. We will know more.
Thank you. And then the second question that was about the use of fibers in the face of rear, in the front of rear face.
Okay. Okay. The main role of the fibers is the preventing the damage. Now it has to do also with the resistance, because one of the modes of failure, and there's more than one, is the formation of a punching cone, similarly to static punching, but under impact. So these failure surfaces of the punching cone can be breached and resisted by the existence of fibers. This means that if we want to prevent rear face damage, which is the most important, this is the protected face, then definitely use fibers in the rear layer, near the rear face. However, preventing damage at the front face may also be important, because we talk about resilience. This has very much to do with resilience in the sense, not in the sense of durability, but in the sense of protective structure being able to maintain its protectiveness even after being hit, even after being impacted. So if there is one impact and then comes another impact, the second impact the resistance against the second impact may depend on the front face damage. And so fibers would be beneficial also there. And in fact, I saw that I showed that RI values in these test series that I showed were largest when we used fibers throughout the thickness of the specimen.
We have 4 more minutes and many more questions are coming, so I'm afraid I have to filter them. Probably, let's see if we manage to answer 2 of them in the last 4 minutes. The first one is, why is there more damage in the double-layered panel?
Why is there more damage?
Yes, from one of the questions. It seems that from your presentation, there is more damage in the double-layered panel.
I'm not sure that I remember such a result. It could be. It could be that, well, if I can open the presentation, we can look exactly at what we are talking. Because it could be that this was a double-layered panel without fibers at the rear face.
Okay. Or did you use a different projectile element in the double?
Well, for each series, we use the same projectile, of course.
Okay. Okay.
The only difference was between the two series of tests. But when we compare the results to our control specimens, then all the other specimens were stricken by the same projectile in the same series of tests, of course.
Well, your presentation is going to be available online. So this is a question that came from the
I would look to see if that particular layer, I suppose we don't have time to look at it now.
Yes, unfortunately, no.
But that particular layer, if it had at the rear face larger aggregates, or it was without fibers, this could be very well the cause for larger damage.
Larger damage, okay. And the last question was about, I posed the question as I receive it, is the material analyzed or idolized as a composite? So this is the trick thing of asking questions that you receive online. So I think that there is not a model yet, so we cannot talk about.
Okay, I will answer this way.
Yes.
When we analyzed our results, we have not used, at least yet, numerical calculations. For numerical calculations, one would have to think how to represent fibers, for example. This can be done in several ways, but I will not go into this right now. We have not done this. What we did do, we used the penetration and perforation formulas, and there are quite few of them. These are empirical and semi-empirical formulas, and there one can incorporate the parameters of each
components,
of each type of specimen in these formulas.
Okay. I think we are just in time to conclude this this first presentation. So I would like to thank you again.
Thank you, Daniel.
Professor, and